We're going to discuss equations of lines and equations of planes. In general, when we talk about equations representing geometric objects, we usually mean a mechanism that allows us to easily check whether a given point belongs to that geometric object or not. We're going to see that these mechanisms that we're going to build are going to work slightly differently for lines and planes. So why don't we begin with lines? So suppose that we have a straight line, and that could be a line either in 2 dimensions or in 3 dimensions. And the basic data that we're going to work with are a point on the line. So let's work in 3 dimensions for the sake of the example. So let's say that you have a point x naught, y naught, z naught belonging to the line. And then you have a vector, a non-zero vector, which is parallel to the line. As we're going to see with this basic data, we will be able to find an algebraic object, in particular a vector valued function, that allows us to describe, to, if you like, identify this line. The idea is pretty simple. If you take any random point x, y, z on the line, then the vector that originates at x, y, z and terminates at x naught, y naught, z naught, which has coordinates x minus x naught, y minus y naught, and z minus z naught, has to be parallel to the vector that has been given from the beginning, has been fixed from the beginning, and happens to be parallel to the line. And pretty much, this allows you to say, at least in a formal way, that the point x, y, z is going to have coordinates x naught, y naught, z naught, plus t times ABC. Or, if we put everything together in one, x naught plus TA, y naught plus TB, and z naught plus t times C. We could write also AT, BT, CT. I think in most cases, it's more common to actually put the variable t, which in this case, we refer to it as our parameter, to actually put it after the numbers ABC. So in general, the way that we can express this is that the line is obtained by using the following vector valued equation. So it's an equation that has outputs that are vectors. So from the initial data that we had, this is how we can find the equation of a line. And we have to make sure that we understand how this equation works. It works as follows. We can plug in real numbers t. We can give t different values, and that will give us vectors. Now, those vectors are, as we have said, free vectors. But there are some cases like this one where we're going to consider them as position vectors. That is, we're going to think of them as originating at 0, 0, 0, which means that in some sense, the idea here can be drawn as follows. So you have your coordinate system, and here you have the line. And pretty much what we have achieved by writing down this vector valued function is we find all these vectors. The interesting thing and that was actually the premise of defining coordinates of vectors, was that once we make sure that the vector originates at 0, 0, 0, then we can identify it, at least numerically, coordinate-wise that is, with the point that happens to be the terminal point of the vector, the point where the vector terminates. So in this sense, we're going to be plugging in values of t, we're going to get vectors, and automatically we can translate them into points that belong to the line. Let's do an example in order to understand how this works. So let's say that we're asked to find the equation of the line that goes through 1 to -2 and is parallel to the vector (1, 3, -4). And to make things a little more interesting, let's also ask the question, does the point at 2, 5, -6 belong to this line? So how are we going to do this? Well, first of all, we're going to use the equation that we gave a moment ago. So let me remind you what it was, because that's all you need to remember. It was that if you have a line for which you know a point, and you have a vector that happens to be parallel to this line, then a vector valued function whose position vectors point to the points of the line are or is a, looks like this: r of t is equal to x naught, y naught, z naught. So we make a vector out of the point. Sometimes informally, I like to call this the vectorization of the point. The vectorization of the point. But certainly that should not be considered to be a term that is widely used. Plus t times ABC. So if we apply this to the present case, then we're going to get that a vector valued function whose trajectory, sometimes we call the points that comprise the terminal points of the position vectors that happen to be the outputs of the function. We call it the trajectory. So in this case, the vector valued function whose trajectory is the given function is going to be given by. So we vectorize the point. So we make it into a vector 1 to -2. And then we add plus t times 1, 3, -4. Okay. And of course, you can always work it out a little more. And this will be 1 plus t, 2 plus 3t, and -2 minus 4t. So, so that's the vector valued function. And now we want to ask, in order to understand how this works, does this specific point that I gave you, 2, 5, -6, does it belong to the line? What should happen for this point to belong to the line? So 2, 5, 6 will belong to the given line if there is a real number t for which R of t is precisely 2, 5, negative 6. Okay. So in other words, you would require 1 plus t to be 2, 2 plus 3t to be 5, and negative 2 minus 4t to be equal to negative 6. And that tells you right away, in general, how hard it is for a random point to belong to a line. I mean, seriously, if you close your eyes and you choose a point completely randomly, and you ask yourself, does that belong to the line that somebody had given me before? I mean, think about it. The answer is no with almost probability 1, or I should say with probability 1. It's just that in the case of such sets, one has to be careful about how to define probability 1. In any case, the bottom line is that it's very hard unless you have almost made up that point so that it belongs to the specific line. Let's see if this is what happens to be the case here. So what you do here is you just solve one of the 3 equations and see if that solution satisfies the other 2. So from the first equation, you get t equals 1. So now the question is, does t equal 1? Is t equal to 1 the solution of the other 2 equations? For the second one, I think the answer is yes. For the third one, the answer is again yes. So it's a big yes. And we can finally answer the second question by saying that indeed, the point 2, 5, negative 6 belongs to the given line. Okay, great. Now let's look at another situation. So what is interesting now is that one can start playing with different scenario. That is, you have data that do not have to be the basic data that we just talked about, meaning this data here, a point on the line and a vector which is parallel to the line, a non-zero vector which is parallel to the line. There could be something different, and you could ask, well, can we, how do we find the equation of the line if the data are not precisely what they are here, but there's something slightly different? So for example, if you ask most people, they will tell you that they think of lines as defined by 2 points. So can we find, so what is the equation? What is the equation? And here again, I mean the vector equation of the line that goes through the points 1 to negative 3 and 3, negative 1, 1. Okay, so in this case, just to see what is given to us, we're given 2 points. Let's call this point A and this point B. So we have point A and point B. So in other words, we have more points than we need because, as we saw before in the basic data that we presented, we just needed 1 point. So we have more points than we want, but we have fewer of the other thing, meaning we have no vector. We just needed 1 vector parallel to the line. So simple logic suggests that you may want to reconfigure this case so that it matches the basic case, the basic data that we need. So we can ask, if we're given 2 points on the line, how do we find a vector parallel to the line? And of course, I believe that the answer is very, very simple. So what you need to do is just consider the vector that starts at A and ends at B, this vector is certainly parallel to the line. So what is the vector AB? So the vector AB is going to be, I subtract the coordinates of A from those of B, and I get 3 minus 1, which is 2, negative 1 minus 2, which is negative 3, and 1 minus negative 3, which is 4. And of course, I should do the correct notation. You just saw that I used parentheses. I should have used diamond brackets because I'm working with a vector. So now I have precisely the data that I need. I mean, actually, I have more than what I need. I have 2 points. And of course, one might ask, does it really matter which point you choose? And the answer is absolutely not. And that's why sometimes it's a good idea to understand that there's not a single equation for this line. So in some sense, it's wrong to say what is the vector equation, but rather what is a vector. Actually, now I have to decide whether I'm going to put A or N because vector starts with a consonant, but let's say that I ignore the vector. So what is an equation rather than the equation? Okay, and of course, we can find the equation now, and the equation is going to be R of t. I vectorize the first point. It becomes 1 to negative 3, and then I put plus t times 2, negative 3, and 4. Okay, and that's the equation, the vector equation, or a vector equation for the line that goes through these 2 points. The truth is that this actually occurs so often. It is so often important to be able to find the equation of this line or an equation for a line that goes through 2 points that I would like to give the general formula, the general pattern. We could have found this formula very easily if instead of working for 2 concrete points, we just worked for 2 general points. So a vector equation for the line that goes through, let's assume that it's not the same point, so through the distinct points. X naught, Y naught, Z naught, and X1, Y1, Z1 is given by R of t is equal to 1 minus t times the vectorization of the first point plus t times the vectorization of the second point. And you can actually see that, I mean, somebody might be a little skeptical of this equation and say, well, why does it work? And it turns out that the easiest way to see that it works is, first of all, it's linear in all the coordinates. So this means right away that it represents a line. And secondly, if you plug in R of 0, you will see that you actually get the vectorization of the first point. If you plug in R equals 1, you get the vectorization of the second point. And we're going to see that exactly this simple fact will be very, very useful later when we will want to parameterize a point, a segment with known endpoints. We're going to use exactly this equation. So I should say that one should actually remember, learn, memorize, take your pick, this equation as much as memorizing the first one that I gave you. So here are the data for this equation, and this is what we get. There is one more point that one should make in this context, and this is going to become very, very useful even in this lecture. And it is, how should I put it? Some kind of reverse engineering. So pretty much what I'm saying is that if we're given a vector equation for a line, say r of t equals to 3 minus t, 2 plus 2t, and negative 1, then it is easy, it is straightforward to find a vector which is parallel to the line. So what do we need to do? All we need to do is look at the process that we used in order to obtain the vector equation for the line, and then we will realize that the coefficients of t, the numbers that are in front of t in each of the components, are going to give us the desired vector when we put them together. All we need to do is read them carefully. So, for example, you have minus t here. So minus t pretty much has what coefficient in front of it? Negative 1. Or when you say minus t, t comes with what coefficient? And the answer is negative 1. You have 2t. And of course, this comes with coefficient 2. And here, there's no t explicitly given in the third component, which means that you have something like 0t, which means you have 0. So if we put everything together, the answer to the question that we just asked would be negative 1, 2, and 0 is parallel to the given line. And this is something that we're going to use many, many times. I would also like to give an example of determining whether two lines intersect or not. So let's give this as another problem. So determine whether the lines R1 of t equals to 3 plus 2t, 5 minus t, 1 plus t, and R2 of t being equal to 1 plus t, 6 plus t, and t have intersect or not. You will see that in the process of determining whether they intersect or not, we actually can find their point of intersection. So it almost goes without saying. And here there's a very, very interesting situation going on here. Most people might look at it for, at least for the first time, and think to themselves that they need to determine whether there exists t such that R1 of t is equal to R2 of t. That's what anybody would think for at first. However, this is not the correct approach. And let's try to understand it. Actually, there's a very simple reason why this is not the correct approach. So the answer to this is no. No, that's not what we should do. And here's why not. So think of the vector equation of a line as describing a motion. Actually, the fact that you were using the parameter t is quite suggestive of what one wishes to do here. So imagine that we use t in order to signify time. Now, so at time t, the first line is at the point pointed to by the position vector r1 of t. And at time t, the second line is at the point pointed by the position vector r2 of t. Okay, so if you ask whether you can find t for which the two equations produce the same point, that would be the same as asking whether those two motions are going to collide. Okay, so the one is one motion, the other is another motion. So the question is, are they going to collide? So at the same time, find themselves at the same point. Yes, but this is not what it means for two geometric lines to intersect. It doesn't mean that there has to be a collision. It could mean that the one line passed, describing a motion, and then an hour later came the other line and passed through the same point, which means that you might want to entertain the possibility that the two lines produce the same point, but for different times. That's why it's not correct to say, let's set R1 of t equals to R2 of t, but rather the correct approach is to say, so instead, we should ask if there exist two different times, so there exist S and T, such that R1 of S is equal to R2 of T. So different times. And now we're going to get the correct system. So it's going to be 3 plus 2S should be equal to 1 plus T. And 5 minus S should be equal to 6 plus T. And 1 plus S should be equal to T. And again, I want you to understand that our chances in a generic situation are pretty much slim. I should say non-existent. Okay, in other words, if you are in 3D space, in 2D space, it's different. In 2D space, two randomly chosen lines will intersect. It's more unlikely that they're parallel, most probably they will intersect. But in the 3D space, two randomly chosen lines will not in general intersect. And that is reflected by the fact that you have to satisfy a system of 3 equations with 2 unknowns. This is what is usually referred to as an overdetermined system. So what do you do in this case? In this case, you solve the system that gives you the consisting of the 2 equations, and you try to see if the solution that you find, the S and T, satisfy the third one. So what do we get? If we subtract the 2 equations, that's the simplest thing to do here. Then we're going to get 3 minus 5 is negative 2, 2s minus negative s is plus 3s, and that will be 1 minus 6 is negative 5. So that will give you 3s is negative 3, which means that s is equal to 3. S is equal to negative 1, sorry. S is equal to negative 1. Okay, and if S is equal to negative 1, then you can plug it into the first equation and get guess T equals 0. So now we could ask, is it true that these 2 solutions that we found for the first system satisfy this third equation? And I guess if you look at it, the answer is yes. Okay, again, these two lines were chosen quite specifically so that they actually intersect. But like I said, generically, it's that wouldn't have been the case. So we can say, yes, they do intersect. And of course, the common point occurs for s equals -1 for the first equation, t equals 0 for the second equation. So if I plug in t equals 0 to the second equation, I guess it's the 0.160 is the point of intersection. Okay, so now let me just repeat how I got this equation. So I said that I pretty much subtract the second equation from the first, subtract. So I subtract the left-hand side of the first. So I get, for example, 3 minus 5 is -2. 2s minus -s is 3s, and so on. Because I know that on the right-hand side, you have t and t, which means they're going to cancel each other, and we're going to find an equation that has just one unknown. This is one standard way to solve a system of two equations with two unknowns in a simple-minded way. Okay, I think it's time to move on to equations of planes. We have said a lot so far, and I think it might be actually a good idea to maybe take a break and review what has been said till this point, and then continue with the second part of this lecture, which is going to be equally intense and where we're going to study equations of planes. But in any case, let's continue with our recording. So now that we have some experience finding algebraic objects that describe geometric ones, and as we saw before, we worked with some typical data. Let's see what the typical data are going to be in the case of a plane. So if you have a plane, our starting point will be to have a point on the plane. So this is what we will require to have. And then a vector, which is perpendicular to the plane. So we have the vector ABC, which is perpendicular. And here we have some interesting piece of terminology. We sometimes say, instead of saying perpendicular, we say normal to the given plane. So if this happens to be the case, so these are the original data, what we do is we take a random point on the plane and see how we can bring all this data together, how we can find a relation between all this data. And pretty much, if we take the vector that originates at the point x naught, y naught, z naught, so I want to take this vector actually. Originates at the point x naught, y naught, z naught, and terminates at the point x, y, z. Then this vector has to be perpendicular to the vector, orthogonal to the vector ABC. So what we're going to have is that the vector that I just mentioned that originates at x naught, y naught, z naught, and terminates at x, y, z. So it has coordinates x minus x naught, y minus y naught, and z minus z naught, has to be perpendicular to the vector ABC, orthogonal to the vector ABC. And what does that mean? That means that their dot product should be 0. What is the dot product? The dot product is a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. And this is the equation that we should know. Okay, so this is the equation of the plane. And let me just mention here that it works in a different way than the equation of the line. So in the case of the equation of a line, we were plugging in values of t and we were finding points on the line. Actually, we were first finding vectors, then points on the line. Here, that's not how it works. Here, a point belongs to the plane. If and only if its coordinates satisfy the equation of the plane. Well, why don't we do an example to see how this works? So let's do an example similar to the first example that we did for lines. So find an equation for the plane that contains the point 2, -1, 3, and is perpendicular to the vector 1, -2, -2. Okay. So this is, and let's give a second question here. Does the point 1, 1, 1 belong to this plane? Okay, so let's see how we're going to answer this. So first of all, a direct application of the formula that we just gave is going to give us the desired equation for the plane. What does it look like? So our vector ABC is this one, our point x naught, y naught, z naught is this one. Put them together and you will get 1 times x minus 2 minus 2 times y plus 1 minus 2 times z minus 3 is equal to 0. Don't forget to put equal 0. Sometimes people just put the left-hand side of the equation. You need to give an equation. You cannot just give one side, assuming that everybody else thinks that, oh, okay, the other side has to be 0. No, we don't know what it would be. You can leave it like that if you like, or you can make it a little simpler. So let's multiply things out. We will get x minus 2y minus 2z. And then what are the specific numbers that you have? You have a minus 2. You have another minus 2. That's minus 4. And then you have a plus 6. That makes the whole thing plus 2 equals 0. Or you could write it as x minus 2y minus 2z is equal to -2. Okay, so that's the equation of the plane that we were looking for. Again, you can give any of these three equations unless somebody asks you to present the equation in a specific form, which I very much doubt. Now, let's answer the second question. Does the point 1, 1, 1 belong to that plane? Think of the equation of the plane that we found as a blueprint for the points that belong to that plane. That is, if I take the coordinates, in this case 1, 1, 1, and I plug them in, let's do it. So 1 minus 2 times 1 minus 2 times 1. I ask, is this equal to -2? Oh boy, I'm afraid the answer is no. Okay, so the answer is no. I genuinely chose this point completely randomly. And of course, that had the consequence that it really had no chances. It really had no hope of belonging to the actual plane. I mean, think about it again. It's pretty much the situation that we described before. Generically, a given point will not possibly belong to a specific plane. Okay. Before we delve into the many interesting situations that can arise in this context, and especially if we start mixing equations of planes and lines together, let me also talk a little about reverse engineering. So suppose that somebody gives you the equation of a plane and you want to know a vector that happens to be normal to that plane. How do you find it? So suppose that we're given the plane 2x minus y plus 3z is equal to 1. Then the vector, which vector? Can you pause the video and guess what vector would possibly be perpendicular to this plane? Just think how we found the equation of the plane before and try to find the answer. So pause the video. And here's the answer. All you need to do is read the coefficients of x, y, and z. So the coefficient of x in 2x is 2. The coefficient of negative y negative y is negative 1. And then the coefficient of z in 3z is obviously 3. So the answer here is going to be 2, negative 1, and 3. So this is the vector that we're looking for. We have to be careful if the letter variables are not on the same side. So in the case of the plane z is equal to x plus y plus 5, a normal vector is given by what? Now, to find the vector, the whole premise was that the letter variables are all on the same side. So in other words, you should bring the z over to the other side, which means that it will become negative z once you do that. So you would get x plus y minus z plus 5 is equal to 0. Once you have it like that, then now you can find the vector, and the correct vector would be 1, 1, negative 1. So what would have been wrong here is to say it's the vector 1, 1, 1, because the coefficient of x is 1, the coefficient of y is 1, and the coefficient of z is 1, but they're not on the same side. They have to be on the same side, and this is what this process just did for us. Okay. There's another remark that we should make here. When are two planes parallel? So two planes in 3D space are called parallel if they do not intersect. So we can also say that they're parallel if they coincide. That's an extreme. I mean, some people might disagree with this because they might say that parallel means that they don't have any points in common, and I think that's formally correct. But sometimes we take the more general perspective of actually having planes that pretty much are oriented the same way. So two planes A1x plus B1y plus C1z equals D1, and A2x plus B2y plus C2z is equal to D2 are parallel, if and only if the vectors A1, B1, C1, and that is the normal vector of the first plane, and A2, B2, C2 are, what do you think, if they're parallel? And it's not so hard to actually realize what the picture looks like. So it's something like this. So imagine that you have a normal vector for the first plane, a normal vector for the second plane. I think the picture is quite self-explanatory. These normal vectors are going to be parallel, and it's also true the other way around. Okay. Now, I would like to look now at different scenario where we find equations of planes or even equations of lines. We're going to mix things up now. But let's begin with something quite important and quite generic. So again, it's how people think of a plane. And maybe the simplest way to think of a plane is as defined by three non-collinear points. So how do we find the equation of a plane if we're given three non-collinear points? By saying non-collinear, I mean that there's not a single line that contains them, because in that case, you cannot define in a unique way a plane that contains those 3 points. So let's try to solve the following problem. So find, again, the correct thing is to say an equation for the plane that contains the points 1, 3, -2, 2, 1, 5, and 1, -1, 2. Okay, so let's say that we want to find a plane. So the picture is like this. You're given a plane that contains these specific points. So again, the question is, how do you go from 3 points, so you have more points than you need, to 1 point and a normal vector to the plane? And I think with what we have seen regarding the cross product, by now everybody should be able to take the right guess. That is, you're going to form 2 vectors, and you're going to take their cross product, and the cross product is going to be really normal to the plane, and that is going to do it. Okay, so let's execute this. So what is AB cross AC? First of all, let's find the points, the vectors A, B, and AC. So they are 1, -2. Again, I'm subtracting the coordinates of A from the coordinates of B. 7 cross with 0, -4, and 4. Okay, and here is the cross product. So I'll delete first row, first column, and you will have -8 plus 28, which is 20, right? Then delete first row, second column, and you will have 4. It's the middle coordinate. You get -4 when you compute that determinant. And finally, delete the first row. And the third column, a 2x2 determinant, is left, which is simply -4. Okay, so this will be our normal vector. Now, if you want to think in a more critical way, you will realize that you can always simplify the vector that you get. So instead of 20, -4, -4, you could just say 5, -1, -1. So I divide everything by 4. I take a vector which is parallel to this just to make my life easier. But I don't want you to think of this as being something necessary. So I'm going to just ignore this simplification and eventually give you the equation as 20. Now, again, we have more points than we need. Choose any one point. It doesn't matter which one you choose. I will choose the first point. So it's going to be 20 times x minus 1. I'm taking 1 from this point right here. Then -4 times y minus 3. I'm taking 3 from that point here, so y minus 3. Plus or -4 times z plus 2 is equal to 0. And that's the given equation. Okay, here I'm not going to give you any, any suggestion that you memorize how this happens or anything like that, but it's a rather straightforward situation. Okay, now let's look at a different scenario. So find an equation for the plane that contains the point 1 to -1 and is perpendicular to the line with vector equation r of t is equal to 2 minus 3t, 5 plus 2t, 1 minus t. Okay, so how do we do this? Well, we have a point already that belongs to the plane. All we need is a normal vector. Let's draw a picture. Let's see what situation we're looking at. So here's supposedly our plane. Here's our point, and here's a line which is perpendicular to the plane, right? So this is the point 1 to -1. Nobody says that the line goes through that point. Okay, I don't know, it might or it might not, but it doesn't really matter. What matters is that I need a vector which is parallel to the line. Why? Because the moment you have a vector which is parallel to the line, it's going to be perpendicular to the plane. And how do we find such a vector? Remember the reverse engineering that we described before. So you look at the coefficients of t in the equation of a line. So it's going to be -3 to -1. So everything now comes into focus. It's very, very straightforward. We're looking for the equation of a plane that goes through the point 1 to -1 and has normal vector -3 to -1. So what is it? It's going to be -3 times x minus 1 plus 2 times y minus 2 minus z plus 1 is equal to 0. I don't think I simplified the previous one. Let's just simplify this one. Like I said before, it's not a necessity, but if we decide to do it, we will get -3x plus 2y minus z, and then let's add up together all the constants. It's going to be -3 times -1, that's 3, -4, that's -1, minus another one, that's -2. So -2 is equal to 0. And of course, you can rewrite this as -3x plus 2y minus z is equal to 2. Okay, any of these three equations, actually, as we said, would do just fine. Okay. Okay, let's look at another situation. So find an equation for a plane, or for the plane that is parallel to the plane 2x minus y plus z is equal to 1 and contains the point one, two, three. Okay, again, here you can pause the video and try to see if you can figure out the solution yourselves. I'll give a couple of seconds before I start working with the solution. But pretty much the situation is as follows. So you have these two planes, and they're parallel. And you know that this plane that you're interested in has the point 1, 2, 3 in it. Okay, so what do you need to do? This plane has equation 2x minus y plus z is equal to 1. So by reverse engineering on the equation of the plane, we can find a vector which is perpendicular to this second plane. What is that vector? Just look at the coefficients of x, y, and z. They're conveniently all on the same side. So they're going to be 2, -1, and 1. So this vector is parallel to the second plane, but since, it's perpendicular to the second plane, but since the two planes are parallel, it's also perpendicular to the first plane. So what do we need to use? We can use this vector, this point, and what is the equation that we get? We're going to get 2 times x minus 1 minus 2. Minus 1. So just minus y minus 2 plus z minus 3 is equal to 0. Again, if you want to simplify it, this will be 2x minus y plus z, and the constants are what? Minus 2 plus 2, that's 0, minus 3, or 2x minus y plus z is equal to 3. Any of these three equations would do just fine. Okay, how about now let's work the other way around. So let's be given the equation of a plane, let's find the equation of a line which is perpendicular to that plane. So here's another scenario. Find the equation of the line that goes through the point 1 to -3 and is perpendicular to the plane z is equal to 2x minus 3y. Okay, so what does the situation look like here? So you have a plane, you know its equation, and then you have this line that is perpendicular to the plane and goes through the point 1 to -3. And you want to figure out what a vector equation for the line is. Again, I should have said find an equation, not just the equation, because there are more than one that one can find. So what do we need to do here? We need to do reverse engineering on this, on the equation of the plane. We have to be a little careful. We need to rewrite this as 2x minus 3y minus z is equal to 0. And once we have done so, then we can clearly see what the vector which is normal to this plane is. It has as components the coefficients of x, y, and z. So it's going to be 2, -3, -1. Okay, so we have our vector, which is parallel to the line. We have a point through which the line goes. So what is the equation of the line? The vector equation for the line, it will be the vectorization of the point, 1 to -3, plus t times the vector which is parallel to this line. We can leave it like that, or we can also write it as 1 plus 2t, 2 minus 3t, and -3 minus t. Okay. Let's look at another very, very interesting situation. Let's ask if a given line and a plane intersect, and if they do, what is their point of intersection? So does a plane 2x minus y plus 3z is equal to 1 meet the line with equation r of t is equal to 1 plus 2t, 3 minus t, 2 plus 4t. Okay, now this is a very interesting situation. I mean, generically, I don't know what the relative position of the plane and the line would be. So I don't know if we will have the very generic situation where the line intersects the plane, or maybe some very strange situation where the line is, as we would say, parallel to the plane. There's another very extreme situation where the line is wholly inside the plane. The bottom line is this, that generically every point of the line is given by points, it has coordinates that are given by these 3 numbers for different values of t. On the other hand, the plane has as its points that satisfy this, the equation of the plane, which is this one, right? So all we need to do is take those 3 components of the line and plug them into the equation of the plane and see if we can solve that for a t. So if you find infinitely many solutions, you are in the case that the equation, that the line fully belongs in the plane. If you find one solution, then the line will just intersect the plane at one point. And if you find no solution, then the plane and the line won't be meeting at all. So what is the case here? So we have 2 times 1 plus 2t minus 3 minus t plus 3 times 2 plus 4t is equal to 1. We need to solve this for t. Let's see if we can do this. So 2 plus 4t minus 3 plus t plus 6 plus 12t is equal to 1. So that will give us a total of 17t is equal to, what do we have on the left? We have 2 minus 3 is -1, plus 6 is 5. Take it over to the other side. 1 minus 5 is -4, which means that t is equal to -4 over 17. We just have a unique point of intersection, and the point of intersection will simply be 1 minus 2 times 4 over 17. So that's, I guess, 9 over 17. 3 plus 4 over 17. So that's 55 over 17. And finally, we have 2 plus 4 times negative 4 over 17. So that will give you something like 34 minus 16. So that should be 18 over 17. Something along these lines. I apologize if one of these was found to be wrong, but this should be the point of intersection, which we can find by just plugging in the value of the parameter for which the line intersects the point, the plane. And there is one last really interesting situation that I would like to discuss. And that's the situation where we want to find the intersection of two non-parallel planes. In general, two planes intersect. That's the generic situation. And the question is, how do we find their intersection? So let's say, find a vector equation for the line along which the planes x minus 2y plus z is equal to 1 and 2x plus y plus z is equal to 3 intersect. Now, you can obviously see that these planes are not parallel, so they have to intersect. Why? Think about it. A normal vector for the first plane is given by 1, negative 2, 1. A normal vector for the second plane is given by 2, 1, 1. I'm just reading the coefficients of x, y, and z. You can clearly see that those two vectors are not parallel. Actually, let me write it, because sometimes when you see something written, you can visualize it better. So I'm saying this vector is normal to this plane. This vector is normal to this plane. Certainly, those are not parallel vectors because you cannot scale the one and get the other. So the planes have to intersect. So how do we find their intersection? Here we have two basic strategies to work with. So to find points that belong to both planes, we literally have to solve this system. And this system is going to have infinitely many solutions. This system is going to have infinitely many solutions. If we find two of them, then we're going to get 2 points on the intersection and we can get the equation of the line. So that's one strategy. And to see how one needs to carry out the strategy, let me say how we can find easily points on that belong to both planes. Here you have a system of two equations with 3 unknowns. And how do you solve it? Maybe the easiest way to just find random points, not to find all of them, just find some random points, is to set one of the unknowns equal to a specific number, and then you're going to get a system of two equations with two unknowns that you can proceed to solve. I think it's very convenient here to, if you look a little at the system, it doesn't matter, it will work with pretty much anything. But I think if I set y equals 0, then I will get a very convenient system because I will have z on both of them. So I will have x plus z is equal to 1, 2x plus z is equal to 3. And you can solve the system simply by subtracting the first equation from the second. If you do so, you're going to get x is equal to 2. Once you know that x equals to 2, then z is equal to negative 3, right, from the first equation, and y is 0. So this gives you right away the point 2, 0, negative 3 that belongs to both planes. So this point is somewhere here. Now, I could do the same thing. Instead of putting y equals 1, y equals 0, I could put y equals 1, and I could get a second point. And once I have my 2 points, I can find the equation of the line that goes through those 2 points. I strictly, I recommend that you actually finish the solution. However, I would like to finish the solution of this particular problem in a slightly different way because it's so interesting. It turns out that you can find a vector which is parallel to the line in a very interesting way. And it's not so much that it's faster, but I would like to just let you think about this piece of information. That vector is simply the cross product of the 2 normal vectors. If you take the 2 normal vectors, then their cross product is going to be parallel to the intersection. So the cross product of the vectors that are normal to the planes is parallel to their intersection. And we have just seen what those vectors are. It's this one and that one. So let's take their cross product. Let's go directly to the determinant. So this is I, j, k, 1, -2, 1, 2, 1, 1. And this is going to be, delete the first row and the first column. You will get a determinant that can be easily computed to be -3. Then delete the first row and the second column. You will get a determinant which is -1. It's the middle coordinate, so put the opposite number, which is 1. And then delete the first row and the third column, and you will get 1 + 4, that's 5. So right away, now we have the data that we needed. So we have a point that belongs to the intersection, a vector which is parallel to the intersection. So the equation that we will get is R of t being equal to the vectorization of the point 2, 0, -3 plus t times the vector that we just found. And this is a very, very elegant solution. I think the fact that the vectors are the fact that the normal vectors to the 2 planes give us a vector which is normal to the intersection is a very interesting fact on its own. You could see it by, open a book up and try to visualize the 2 normal vectors that come out of the plane. Then you will clearly realize that the intersection, so think of the planes as the 2 pages of the book, then you will realize that the intersection is actually perpendicular to both of these vectors, establishing this remark that I just gave you, which is a very, very interesting remark. So with this, we come to the end of our lecture. Actually, there's one more thing that I would like to say here, which is what are the very, very simple equations of planes that are parallel to the coordinate planes. So for example, if you look at planes that are parallel to the xy plane, this is the xy plane, then in general, they will have equation z is equal to a. If you're looking for planes that are parallel to the xz plane, this is the xz plane, then they will have equation y is equal to a, again, some number a. And finally, if you're looking for planes that are parallel to the yz plane, this is the yz plane. Then they will have an equation that looks like x is equal to a. And with this, we come to the end. Thank you for watching.